Welcome everybody to SoCal our user groups meetup. We're very excited for today's presentation. So John, do we have any announcements that we need to go over?
It hasn't been announced yet, but in early October, we will have a statistics course on advanced regression in R. That will be a full day course held at UCI, a nominal fee of like $10 or something like that. And we'll give you lunch. Yeah. So I'll post that soon.
Great. Sounds wonderful. And so we would like to thank the UCI Paul Mirage School of Business for their continued support, as well as the UCI Master of Data Science program. And here's all of our contact information, especially for the people who are new here for the first time. If you want to connect with us on Slack, you can find us there. All the previous talks are on GitHub. And without further ado, I'd like to get to the meat of today's presentation. So we are so excited to have Vincent Arelbundock here. Did I say that correctly?
Perfect.
Okay. So he's coming here from Montreal, where he teaches research methods and political economy in the political science there. And he's the author of several wonderful packages. Many of you may know Model Summary. This talk is going to mostly focus on marginal effects, and I am really excited to learn from him. He has got the package website has a lot of vignettes, and very well documented, so I'd highly recommend it. And yeah, without further ado, thank you so much, everyone, for joining, and thank you, Vincent, for speaking to us tonight.
All right. To do the screen share. There we go. Well, thanks so much for the invitation. I'm very pleased and excited and a little bit nervous because I rarely do presentations like this for technical audiences. So this is going to be a new one for me. But it's going to be a fun one because I can show a lot of code and you'll all get to hopefully learn a little bit. So just a little thing first, I'm on a tiny screen, so I might not see hand raised or if you move on the screen or if you want to ask something, I won't see you. So you should just open your mic and ask questions mid-presentation. I am happy to entertain all the questions. Okay, so this is a talk about marginal effects, which is a package I've spent way too much time writing in the past few months. And I think it's now at a point where I'm kind of proud, I should say, about this package now, because I think it's gotten pretty flexible and it's kind of neat. And anyway, I like it, and I hope you will like it too. So the point here is I fit a model on what? Well, the package is about post-estimation procedures, and it basically helps you interpret the results of your model. And okay, I'm getting signals that I'm talking too fast from the people in my room here. Okay, it's great to have local help. All right, so that's about me. I am a Quebecois, yes, and then after spending most of my life in Montreal and in Quebec, I went to study.
Did I jump scare you?
Yeah, a little bit. You did scare me. So I went to study in the US for a few years, and now I'm back in Montreal teaching political science, as Rebecca said. So I've been contributing packages to R, to CRAN for a little while, since 2009. But I would say that these two last packages that I wrote, the model summary, which is for regression tables and data summaries and that kind of stuff, and this new one, marginal effects, are really the bigger contributions, I think. So that's about me. And now for the problems that I'm trying to solve. Okay, so in R, you can fit a bunch of different packages, a bunch of different models with a bunch of different packages, and a lot of them produce rather inconsistent objects. And it's kind of difficult to get a read on those objects. It's really difficult to know how to handle them and how to post-process them once they're fit, right? Once you have your model, what do you do with it? You can, of course, call summary on most of them, and that will give you something, maybe coefficients, maybe something else, but it's not clear how you go about interpreting this. And just to illustrate this, I'm showing here two models. So the first one is just a basic logit model fit with the base RGLM function. And then the second one is a multinomial logit that I'm using the same empty cars data set that I'm sure a lot of you know. And so what I'm doing here is I'm fitting two models, and then I'm doing predictions on those models. So the predict function is a very standard function that a lot of you have interacted with. And I'm going to ask for standard errors around those predictions, and I'm going to ask for predictions on the response scale, right? So that's pretty standard stuff so far. And I have two objects, one called pred1 and one called pred2. All right. So what do these objects look like? So if I look at the structure of the pred1, what I have actually, that's the prediction for the logit model. So what I get there is a list with three vectors. The first one is the predictions fit. The second one is a standard error for that fit, right? So when I say predictions here, what I mean is fitted values, essentially. That's synonymous for me. So you get this list of three elements. But when you do the same call to predict on the multinomial logit, what you get instead is a matrix of predictions. That's the number of rows is the number of observations, and then you have three columns, which is kind of weird if you don't know what to expect, and you don't get standard errors. So there's this fundamental inconsistency there. There are good reasons why it's inconsistent, but the point here is that this is difficult for users because the models, the objects are inconsistent. The second problem that I'm trying to solve here is the problem of interpretation. So I have the first model, which is a logit. I have the second model, which is a multinomial logit. And I do summary on these two things, and this is what I get. So on the left side, you have the logit, and on the right side, you have the multinomial logit. So if there's like one statistician in the room, that person probably says, all right, those are log odds. I know how to interpret this. It's pretty easy and normal. But for the rest of us, a log odd is kind of a confusing quantity, at least for, maybe I should only speak for myself, but I don't personally know what it means substantively, what it means for the real world, this quantity. And so this is a real problem. You have your fit, you have your model, but you don't know how to interpret it. You don't know what these quantities mean substantively. What does it mean for your action for your decision that you're going to make, what it means for the inference, for the scientific question that you're asking. So this is the second problem, the problem of interpretation. So the solution here that I'm proposing is this package called marginal effects. So the idea for interpretation is that I'm going to offer a bunch of post-estimation methods to interpret your statistical models. So these are just going to be very simple functions that you're going to call on your model object and that are going to help you interpret the model. And then there's the problem of consistency that I'm trying to fix. So I'm going to suggest 5 what I call general purpose technologies that you're going to be able to apply to basically any model you want. And using these technologies, these functions, you're going to be able to interpret a very vast array of classes of models. So we're close to 70 classes of models supported. And I say classes of model because a class here is also a pretty vast array of model itself. So there's a lot of flexibility here, and it's all done with one consistent interface. All right, so there are alternatives in this space. So the main one that you should know about is probably e-means, which is old and robust and kind of wonderful. And it is also the most popular alternative. So if you're really looking for something else than marginal effects, that's probably what you should look at. It's also quite popular, more popular than my package. So that might be important. There is, I think, still a feature gap between the two packages, but it's closing and in some aspects reversing, where marginal effects can do some things that e-means can't. But anyway, you should look at this one. Then there's margins. Maybe some of you have played with that. And then there's these other two packages, model-based and GG effects, which are really cool, super easy to use. But they're basically wrappers around e-means with a few more functions. So try them out. They're great. Yeah. All right. So if there are alternatives, why marginal effects? Well, I did make an effort to make this package very simple, powerful, composable. I think that's really important, the composability. And what I mean here is that the arguments of the functions, basically all the functions have the same arguments, and you can compose and combine these arguments in really interesting ways that make for really powerful things. So it gives you a lot of opportunities, I think, and it's composable within the package, but also all the objects that the package produces are super standard, like data frames in long format that you can just plug into ggplot or something like this. So it's very easy to combine this with other tools. The other important thing that I want to underline here is that the results are mostly valid, I hope. And I try to ensure that by doing pretty extensive tests, by checking the results against external software like Stata or eMeans or some other packages. So I've done quite a bit of effort for this. And I spent a lot of time on this, and it's going to be developed actively for the foreseeable future. So keep your eye on it. All right, so let's jump into it. Should I stop? Are there questions so far? Or are we good? Or?
There are not, but I did want to ask you what you would like, how you would like questions to be done.
Yeah, you can. People can just interrupt me. It's good whenever. Yep.
Okay.
That might be preferable, actually, if there's a sticking point we need to handle it.
Okay.
Okay. So these technologies that I'm going to introduce, the first one is the delta method. That's pretty standard. Most of you must know this, or some of you should. Then adjusted predictions, that's fitted values, contrast, marginal effects, and then marginal means. And I'm going to illustrate these technologies, these functions, using one of the data sets that are uploaded on this website that I built a while ago called R Datasets. And that's just a plug for the website. If you're looking for example data, you might want to visit that. It has almost 2,000 free data sets with good documentation. And basically any kind of data you might want is there. It's really great for teaching or for trying out software. Recommended from me, by me. Okay, so this is the data I'm going to look at today. It's the affairs. It's a survey about the number of extramarital affairs from 1969. So we have the number of affairs in this column here, and then the gender of the respondent, the age, the number of years they were married, whether they have children, etc. So I'm loading this data set in memory with read CSV. And then I'm going to fit a model, which is a Poisson model. It's just a standard GLM function with the family Poisson that you can see here. And I'm going to summarize it. So maybe some of you really know the Poisson model very well, and you're able to interpret these coefficients straightforwardly. Not everyone can, but I'm going to give you tools to do that easily later. Okay, so what is the delta method? So that's kind of abstract, but I'm going to show you very concrete examples. So the delta method is a very general strategy that can be used to compute standard errors for functions of parameters. Parameters here can be model coefficients, predictions, a bunch of stuff. Okay, so here's the example. So remember, I had this model of affairs. So the dependent variable is the number of affairs that someone has. And the explanators are whether someone has children, whether that person is a man, and the number of years that they are married. And I call coef, so I get the coefficients of my model here, right? So what I notice is that these two coefficients, the gender male and the children yes, they're pretty close to each other, right? 0.038 and 0.030, right? So these are pretty similar coefficients. So what I could do with the delta method is a test of equality. So I could say, I could ask, are these coefficients equal? So that would be my null hypothesis, that these two coefficients are exactly equal. So what I do is I use this delta method function. I give it the model. And then I do the hypothesis is that children, yes, is equal to gender male. And that's going to immediately compare the two coefficients. So if you look at this estimate here, that's 0.008. That's exactly the difference between the two coefficients of interest. right? 0.038 minus 0.030. That's the difference here. And it gives you a nice standard error, the p-value, the confidence interval, and all that. So that's the delta method. It's a strategy to give you standard errors around functions of parameters. So I can specify the hypothesis in this way, right? Just by giving the names of the coefficients, or I can give you the index of the coefficients. So that's the position of the parameter in my vector. So children yes is the second coefficient, right? There's the intercept, then there's children yes. So I do B2, that's coefficient 2. Is B2 equal to B3? And that's exactly the same hypothesis that I specified above. I'm just showing you this alternative syntax that's available because it's going to be useful later in my examples. Just for information, there's also this other alternative syntax that you can use. And this is by passing a vector of a numeric vector of the same length as the number of parameters. And this is basically a linear combination of the coefficients. So and you can pass matrices if you want to do various custom contrasts. So this is just for the more advanced users possibly. This could be of interest because you can do a lot of really cool things with these linear combinations. But that's the 0, 1, minus 1, 0 is exactly the same hypothesis that we tested just above. If you look at the estimates, they're all the same. This is just
Hey, Vincent.
Yeah.
I can see a use for the third case, but what would be a use case between the first and the second?
So you'll see it in just a few minutes. So the hypothesis argument is available in all the functions of the package. And in some cases, you don't have term names. So you can't really just do children, yes, equals gender male. So you actually have to give them a positional index like this. And it's going to be this B2, B3 syntax.
Okay. And what determines the positional index? Basically alphabetical?
So it's,
intercept first.
It's always in the order that the summary comes out in, basically. So in this case, it's in the order that CoF gives you. It's as simple as that.
Okay, thank you.
Okay, thanks for the question. But I'm going to give you an example later, and I think it's going to be clearer. And then just one last thing that you can do, and this is kind of crazy and silly, but this is a hypothesis with a weird nonlinear function. So this is just to show you that the method is quite general and powerful, and you can do a bunch of crazy things with it. So this is interesting because this delta method function basically gives us standard errors everywhere for all the other functions of the package. So that's kind of the core component of marginal effects. And this is going to give us a lot of what I talked about when I said composability earlier. I'm not even, yeah, okay. So all the marginal effects function will have this hypothesis argument. And we're going to be able to ask a bunch of questions. So in this case, it was, were these two coefficients equal? But we're going to be able to ask the same thing about two predictions, for example. Are these two predictions equal? Or are two contrasts equal? Are two marginal effects different by 5 units or something like this? So we're going to be able to use that to great effect, I think. Okay, so this is the delta method. The second technology that I want to introduce is adjusted predictions. So adjusted predictions are just this. They're predictions. They're basically fitted values. You know what it is, right? So predictions can be made on the original data set, or they can be made for user-defined values. You can just create your own fake data and do predictions on this. So the normal way to do predictions in R is like this. So we have our Poisson model, that's mod, and we do predict. And then we get one prediction per respondent, per row of the data set, right? So if I can scroll down here and see all the predictions for all the respondents. Okay, so that's the base R way of doing predictions. In marginal effects, what you do is you do predictions instead of predict, it's predictions, and you do mod. And instead of getting just one number per row of the data set, you get a full data frame where each of the original observations get their prediction, standard errors, confidence intervals, etc. So I can also scroll here. You have all the units there. So this is kind of neat. Then you can do predictions on a user-specified grid. And I've introduced another function that's called data grid. That's just a convenience function to help you build grids of predictions, essentially. So in this case, what we do is we do data grid years married equals 1 or 25. And what you'll see in this result here is that we've made one prediction at the top for someone who's been married for 1 year, and then another prediction 4 affairs or 4.8 affairs for someone who's been married 25 years. So it looks like the person who just got married has less affairs, fewer affairs than the person who's been married for 25 years, right? So this is kind of already quite nice to interpret your models. You think about the individuals or the types of individuals that you care about, and you make predictions for them. So this is quite useful. The data grid function is quite flexible. So what you can do, for example, is instead of specifying that you want years married 1 or 25, what you can do is pass a function. So you say, you pass the function range, which gives you the minimum and the maximum value of any vector. So that's a range is a base R function, right? Everyone has access to that. So you pass the base R function range, and what it does is it does the predictions for years married 0.125, and then years married, I'm guessing the number is something like 15 here. So that allows you to create grids very easily. And with this data grid function, all the variables that are not explicitly specified are held at their mean or mode. All right. So now we can move on to the very cool stuff. So this is the same prediction I made on the last slide. It's just a prediction of the number of affairs for the minimum and the maximum value of years married. Okay, this is what it is, and I have my 2 predictions here. And now I can ask, are these 2 predictions equal? Is the first prediction of 0.7 affairs really that difference from 2.22? Because there's uncertainty, there's a standard error that we need to take into account. And so what I do here, and this is the example I was talking about, John. What I do is I do the hypothesis B1 equals B2, and here B1 is the row of B, basically, right? Or it's the row that I want to compare. Okay, so I want to compare the prediction in the first row to the prediction in the second row, and I want to test the null hypothesis that these 2 predictions are equal. And what I see here is that the difference in predicted values is 1.52. And if you just do the first one here minus the second one there, you'll see that it's 1.52, and you have a standard error around it. So this hypothesis argument works for all the functions in the package, and you can do some cool comparisons like this. All right, so there's also some plotting functions in the package. So this is plot cap, which is plot conditional adjusted prediction. And so what I do here is I plot the dependent variable, which is the number of affairs, with respect to years married and children. So you can see that these are the prediction, the predicted values for the dependent variable as it changes for different variables, and it's pretty plot. And this is just a standard ggplot object, so you can use facets, you can change the colors, you can change the scales using all the normal ggplot functions. Okay, so something else you can do with this predictions function is take average predictions. So if you just call summary on the predictions object, you'll get the average prediction. So if the process would be this. So if you make predictions for every single row in the original data, and you average those predictions, then you would get something like this: 1.4 affairs on average in your data. This is average predictions. You can do this by subgroup with the by argument. So I want to calculate the average predictions in my original data set for the individuals who have children and those who don't. And again, you see that there's a difference between these 2 groups. And I have confidence intervals and all that. So that's also quite useful. We can do predictions on different scales. This is maybe not so important, but we can do on the response, on the link scale. a bunch of different things.
Vincent, before you go on,
yeah.
there's a question in the chat. It says, is this like a PDP or a bit different?
What's a PDP?
Partial dependence plot?
Oh, yes. So partial dependence plot. Yeah. So this is the same. This is similar. So what we're doing here is we're actually holding all the other variables at their mean or mode. So this is conditional on the mean of the data set, essentially. Does that make sense?
Makes sense.
Okay.
Can I throw another quick question in?
Sure.
Can you give a really brief answer on why there's standard errors everywhere? Do you actually have closed forms for all these linear combinations so that you can calculate that? Which seems crazy for such a large class of models. Or are you secretly bootstrapping behind the scenes, but that would be too expensive? So I'm confused.
No, so this is all, yeah, no, you're right. So some of these standard errors are not well defined. And what I'm doing here is I'm just applying a very simple delta method strategy to compute the standard errors by doing I mean, you know what the standard error, the delta method is, right? I calculate the Jacobian by shifting the coefficients of the model a little bit. So that will give you standard errors for pretty much all these quantities, but I can't make guarantees, of course, that they will be well behaved for all the models. So yeah, I guess I abdicate my responsibility there. So maybe it's a bit irresponsible on my part. But that's a good question.
Yeah, no, I'm familiar with the adding a delta to the parameters and looking at the outcome, but that's how you get the shift in the outcome. Where does the standard error come from?
No,
so inspired this evening.
I'm sorry. Can you repeat that?
Yeah, no, I'm not I mean, I see where the difference comes from and why we do the delta method, but I'm not seeing where the second moment comes from, or the the variance or the standard error.
Yeah, so I have a vignette on how I calculate the standard errors. And how it works is that you shift not only, so you don't just shift. So say, for example, now we're just doing predictions, right? But in the other case where I'm going to do contrasts, that it involves a shift in the outcome variable, of course, but that's not what I'm talking about shifting here. What I'm talking about shifting is that what I do step by step is something like you take the model object and then you shift one coefficient by a tiny amount, and then you see what your quantity looks like in the end. That gives you one column of a Jacobian, right? And then you shift the second parameter by a tiny bit, where so you're taking the derivative with respect to the coefficients of the model, not with respect to the regressors. And so that gives you a Jacobian, which you can plug into your delta method in the end. So this is where the second moment will come from. Maybe we can talk offline about this, or I can refer you to the vignette. Is that okay? Yeah. I just need validation. I'll be thrown off course otherwise. All right. So this is average predictions. And then okay. And then the other thing that I would just add on the last point is that this is not an exotic strategy. All the standard errors are validated for almost all of the models against theta and against e-means, and that's basically what everyone does in this space. Okay. So now that we've done predictions, we're moving to contrast. So what is a contrast? I use this quite loosely to mean the difference, a ratio, or some other function of two adjusted predictions. So we had predictions or fitted values before, and now we're going to do a difference of two adjusted predictions that we'll have calculated for meaningfully different values. Okay, so contrasts are super important. So if there's one thing that you probably will care about in this package or in this talk is the contrast function that I call comparisons. That's the name of the function. So you can have some questions like this. So what's the difference in predicted cholesterol levels between people in the treatment or the control group? And then that's a really important question, obviously, for medical researchers. What happens to predicted Y if X increases by 1 standard deviation? Or is the estimated probability of conversion higher if the customer sees a blue shirt instead of a red one? So those are all very profoundly important scientific questions, maybe not the last one, but commercial questions, certainly. So these are the kinds of questions that the contrasts help you answer. So to understand contrast, I think for me, code explains these things quite well. And I'm going to show you step by step how you would go about calculating a contrast with base R functions. So this is kind of a dumb approach, but it's a simple one. So first of all, I take my affairs data set, and then I create 2 copies of it, the dat no and the dat yes. Then I will set different values of the predictor of interest, which is children. That's the value that I care about. That's the predictor that I care about. And in the first data set, all the values for all the observations will be no. And in the second data set, everything will be set to yes. Then I'm computing predictions on these 2 different data sets. So you'll notice that the key here is the new data argument. In the first case, I only take the data where children is no for everyone, for all the observations, and then I take the data where children is yes for all the observations, and I do the predictions for all these observations. So P no here is just a vector of predictions, a vector of fitted values, and PS is a vector of fitted values as well. And it's what's important here is that the PS is the fitted values if in the counterfactual world where everyone had children. And the P no is the vector of predictions in the counterfactual world where everyone has no children. Okay, so now we have these, sorry about that. Now we have these 2 vectors of predictions, and we're going to compute the contrast for each individual. So it's just P yes minus P no. And what this says here is that for the first observation, if that person had children, I would predict that this person would have 0.05, 0.06 more affairs than if they had no children, right? So that's the difference in prediction. And these numbers here, the gap between the difference between these 2 sets of predictions, I call a contrast, okay? So what you can do is redo all of these same steps, get the contrasts, but instead of calculating 1 contrast per unit, 1 contrast per respondent in the survey, then I calculate the mean contrast or the average contrast, which is 0.06. So on average, if you have children, then you should have about this amount more affairs than if you didn't have children. That's the comparison between these 2 counterfactual worlds. Okay, so this is the manual way. With marginal effects, you use the comparisons function, and you just do comparisons and then your model, and then it computes the same quantity, but it does it for all the variables in the model automatically, and it gives you nice results like this. Okay, so this is just a very simple way to get your contrasts. And you can do a bunch of things. So with the variables argument, for example, you can specify the kind of contrast you want. So you might want to say, I want to compare the number of predicted affairs for someone who's been married 25 years relative to the number of predicted affairs for someone who's been married for just 1 year. And then the gap between these the predicted affairs for these people is about 4, right? And there's a standard error and confidence interval. You can do different things, like instead of saying I want to compare 1 and 25, you can say I want to compare a change of 1 standard deviation in the number of years married. That could be very interesting. So this is a very simple contrast, which is just a difference between adjusted predictions. So it's just y hat 1 minus y hat 0. But you can do basically anything you want here. You can have two sets of predictions, and you can take exponentiate the difference. You can take a ratio of predictions. You can take a log ratio. You can take odds if you want. So the function comparisons has a bunch of shortcuts like this that allow you to do different comparisons, different functions of predictions. But you can also specify arbitrary functions of this high and this low prediction. So if you look at the function here, the high would be predictions for people with children, and the low would be predictions for people without children. And I can compose any function that I want to compare these things, right? So this allows you to do things like adjusted risk ratios and way more. Okay, so this is contrasts. Now we can move on to marginal effects. So what is a marginal effect? This is very complicated because people use this expression to mean a ton of really different things. It's super inconsistent. It's super annoying. In this talk, I'm going to use the expression marginal effect to mean a slope of the regression equation, right? So this is what I mean here, but marginal can mean very different things. So just stick with me. Marginal effects is a slope. So in the simplest linear models, the marginal effect is just a coefficient, basically. So if you take the partial derivative of y with respect to x, then you just get beta. So that's very simple. But in more complicated cases, you may need some numerical derivatives, which we do here automatically in a very kind of naive and simple way, but it's done for you. So maybe you want to take it. So this is a nice thing, marginal effects, because it gives you a slope. It gives you the instantaneous effect, or the effect of a very small change on x of x on y. And this works for a bunch of models. There's a lot of classes supported. So how it works in practice. So let's say I fit a model like this with maybe an interaction, something like this, HP times WT and the MT cars data. I fit this model, and then I call the marginal effects function, and then I do a summary on this. Well, this gives me the slope with of the response with respect to HP, which is a negative slope, and then the slope of the response with respect to WT with weight, and it is also a negative slope. So this is cool. We can do this for models with interactions or with smooths or with whatever. It's very flexible, and it gives you at least some measure of the effect of X on Y. So some things you can do is do elasticities instead of just the slope. A lot of economists like to do this. So that's convenient.
Can you explain what elasticity is? I'm not familiar with that.
Right. So here, elasticity is a transformation of the slopes, which allows you a different interpretation of the results here. So for example, when you talk about the elasticity of HP here, it would be interpreted something like a reduction of X% in the predictor is associated with a change of X% in the outcome variable. So it is a percentage change of the X and a percentage change of the Y. So that's what elasticity is here. And you can also have a semi-elasticity. So you can have a percentage change of X affects just a unit level change in Y. So it's just a convenience for different interpretation that you may want to look at.
Thank you.
So all the functions like this one as well, marginal effects, has the plotting functionality. So in the model before, there was an interaction between HP and WT. So what you can look at here is the marginal effect of HP on the dependent variable. And that marginal effect is the slope. But since there's an interaction in the model, this slope changes with different values of the WT variable. So this is kind of a neat way of showing this in a graphical form. Okay, so I've talked so far about the delta method. I've talked about predictions. I've talked about contrasts. I've talked about slopes. There's also this whole set of function for marginal means that I will skip now. But this is really the emphasis of the e-means package. So if you've worked with this, you've looked at marginal means, and we've replicated a good chunk of the functionality, but not all. But this is something that you can ask me in Q&A, or maybe go read the vignettes. Okay, so I just want to highlight a few things. So if you have a weird model, there's a good chance it'll just work. So for example, here's a model from a blog post by Andrew Heiss, who studies the effect of autonomy of opposition parties on freedom of the press. And he fits a Bayesian model with random effects, with BRMS, which is kind of an amazing package. But that's what he does here. It's rather, well, I guess it's a simple model, but it's still like there's two formulas in there, and then there's some random effects and different family of distributions here. So how would you go about interpreting this? Well, the good news is that all the functions that I've shown you before work just as advertised before. You basically don't need to change anything. So you can do predictions by region, for example. So you get the average predictions for Asia and Pacific. You get all the regions like this, and then you get credible intervals with that. You can do the slope of the outcome function like this. So you have the derivative here of your response, which is very cool. But what's really nice is that you don't need to change anything, right? It's just the same function call as before. You can, if you're a Bayesian, you may care about this. You can extract the posterior draws super easily. You just call the function and then do this posterior draws, and then you can plug this right into ggplot and plot your distributions, your posterior distributions like this. So this is nice. This is an example of another weird model, a GAM model with some smoothing terms. And again, so all the other functions, predictions, comparisons, marginal effects, they all work. And that also includes the plotting functions. So in this case, I'm plotting the predictions, the outcome variable y, over time as it changes. So that's what you can do. The package allows you to use robust standard errors thanks to the awesome sandwich package. So this is in this example here, I'm using the VCOV argument, and I'm specifying the right side only formula with one variable there, and that says I want to get the cluster robust standard errors based on these clusters of the cylinders variable. And the standard errors are adjusted automatically there. You can do tables. So this is a plug for my other regression tables package. So you have two models here, just a linear regression and a logit model. And I print them in one table side by side, and you'll see, of course, that the OLS coefficients are very different than the logit coefficients because they are very different quantities. It's not surprising. But when you do marginal effects, so I just take my list of models, right? Here, I just stored the models in a list. I just take my list of models and I do a lapply, and I just apply the marginal effects function to all the models in the exact same way. And then I just plug this into model summary automatically. And automatically the table comes out and it looks pretty nice. And you see that the slope actually for these two models, the slopes are really not that different in the end. So the coefficients themselves are different, but the coefficients can sometimes be hard to interpret, but the slope is comparable for these two models, which is interesting. All right, so some more advertising for model summary. I was lucky enough to be accepted with this article in the Journal of Statistical Software. Just came out, so go read that. Model summary does a large range of different tables. So you can have balanced tables, you can have summary tables, you can have fancy LaTeX table. tables. You can have tables with histograms in them. There's a lot of stuff you can do, and it's quite flexible. Okay, so back to marginal effects. I just want to highlight that I wrote a lot of words in these docs, and there's a lot of case studies, some contributed by people, for which I'm very grateful. So go read that, and if you have questions, ping me on Twitter or send me an email. I'm always happy to talk about this stuff. And finally, thank you to the people who wrote the dependencies on which I rely. R, of course, but also data table, checkmate, which is a super cool package. Go check that. And then insight, without which none of this would work. It's a really cool package that provides a set of standardized extractors. So let's say you want to get I don't know, the number of observations for some weird model where the knobs function doesn't work. Well, this one will probably work. Whether if you want to get the number of degrees of freedom, you can get that as well. It's all a standardized way to extract objects from basically any kind of model. And then the contributors, and then you, of course, for showing up here today. All right, I'm done. Thank you.
Thank you so much. That was wonderful.